All right, welcome everyone. So as far as announcements go, Maria just pointed out that I did not actually post the data set that you need for problem 1 on the written homework assignment. Sorry about that. I will get that posted after class today. As a reminder, tomorrow for lab, we will have a regular lab doing some practice with non-parametric tests and possibly also with some categorical data. But if you have time at the end of lab, you are welcome to work on your project in lab and ask me questions about that. And then next week during lab day, we'll have our project work day. So you can budget your time working on the project outside of class based on that information. We do have a final exam in this class during the final exam week. That's going to be online like the 2 midterms have been. What I think I'm going to do is open it up so it's available for 24 hours on the day that our final exam is scheduled. So that way you have some flexibility in there, but also it doesn't become a burden where you have to put it off and then schedule it around other exams. Are there any questions about sort of the logistics for that? All right, I will get a practice exam posted on Canvas by the start of next week. All right, so when we left off last time, we were talking about non-parametric tests, specifically the Wilcoxon signed rank test. And we had seen that for our example data set about whether a particular diet is successful in helping people lose weight, we ended up with a test statistic of 5.5. So remember how we got that was we took the differences in each pair. So this is the non-parametric equivalent of a paired t-test. We eliminated the rows that had a difference of 0. And then we ranked the absolute value of the differences. So the smallest difference would have gotten a rank of 1. Actually, it was a tie between 2 values that were smallest, so they got a rank of 1.5, the average between 1 and 2. And then our test statistic, this was a one-sided test, so our test statistic was t minus the sum of the ranks of all of the values with a negative difference. So this -1 gives us a rank of 1.5. And this -3 gave us a rank of 4. So our test statistic was 5.5. All right, so now we need to use this test statistic to come up with an approximate p-value to be able to say what our conclusion is. So the way we do that is looking at table 9 in appendix 3 in the back of our book. And we start by finding the column that corresponds to our sample size. So this is the sample size after we've eliminated the rows with zeros. We had a sample size of 14. And we look down to see where 5.5 falls in this table. So we see that it's less than the smallest value in this table of 13. And for a one-sided hypothesis test, 13 would correspond to a p-value of 0.005. So here we can say that our p-value is less than 0.005. So another way of saying this is that for n equal to 14 and a significance level of 0.005, t sub 0, so the threshold value, the cutoff that would give you a p-value of 0.005 would be 13. And 5.5 is less than 13, so our p-value is less than 0.005. So there's enough evidence at the 0.005 level to claim that the median weight loss in the population of people on this diet is greater than 0. So remember that these non-parametric tests are about the shape of the distribution or about the median, not about the mean. So that's a way in which they're different from their parametric equivalents of t-tests. Questions about this example? All right. To do this test in R, you would use the function Wilcox.test. So you can do this in two different ways. One way would be to compute the differences. Say alternative equals greater, so we're specifying the direction of the alternative hypothesis. And then say that we're testing the null hypothesis that mu, so the median, is equal to 0. And that gives us an approximate p-value of 0.0017. So that is in fact less than 0.005, which is what the table told us. The other way you can do it is by putting in the values before the diet and after the diet, and then using paired equals capital T for true, or you could use the word true in all capital letters. So as far as choosing your type of test, if the population is normally distributed or the sample size is large enough, then doing a t-test, so a parametric test, is going to be more powerful than a Wilcoxon test. Can someone remind us what it means to say that the power of a hypothesis test is 0.8, for example? Niall?
Is it the confidence of type 1 error?
No, it's not the confidence in the type 1 error.
The complement.
Complement. No, it's the complement of a type 2 error. So the power is your probability of successfully rejecting the null hypothesis when the null hypothesis is false. So because we're conditioning on the idea that the null hypothesis is false, we're in the world of it could be a type 2 error, but the power of 0.8 would be we have an 80% chance of avoiding a type 2 error. Isaac.
Probability that you reject the null given that the alternate is true.
Exactly. Yep, that's another way to say it. So this is saying that if a t-test is appropriate, then you're better off using a t-test than a Wilcoxon rank sum test, because that gives you a better chance of rejecting the null hypothesis if the alternative hypothesis is true. All right. Another thing to keep in mind here is that because the process of doing a Wilcoxon rank sum test involves removing zeros, that can bias your results a little bit in favor of the alternative hypothesis. So that's why R gave us that warning on the previous slide about cannot compute the exact p-value in the presence of ties. So in that case, especially if you have a lot of ties, it may be better to use a permutation test instead. So if that's something that you're interested in, feel free to stop by office hours and I can provide some background about that. Are there any questions about the Wilcoxon signed rank test? All right. I think that's all I had to say about that. Let's talk about the Mann-Whitney U test, otherwise known as the Wilcoxon rank sum test. So to get us started with this, take a look at parts A and B of problem 1 here. So Vivian, this is the Mann-Whitney U activity. The zero might be relevant, but explain why it's relevant. the sign rank test that we just talked about. Some parametric tests are is that a situation that we're in? No. There's no particular care. Each person in class one or one person in class two. All right. So for problem A, why isn't a 2-sample t-test a good choice for this data set? Sam? Yeah, the sample size is 10, 5 in each sample. So pretty small sample size. Kyle? Yeah, it looks like this 0 is an outlier. So that's further confirming that we can't rely on a normal distribution or a t-distribution for our test statistic. And because our sample size is small, we don't have enough data points for the central limit theorem to kick in and tell us that the test statistic will still be a t-distribution. How about the Wilcoxon signed rank test that we talked about on Monday and at the start of class today? Why isn't that appropriate here? Isaac?
They're not quite like matched pairs. We don't know which ones match up with which.
Yeah, as far as we can tell, these rows were just there for convenience of not having the data set be really long. There's no particular pairing between this person in class 1 with this person in class 2. So this isn't a matched pairs situation, which is where we would use the Wilcoxon signed rank test. So here's sort of a summary of what we just talked about. If we have a 1-sample t-test or a paired t-test, the non-parametric analog of that would be the Wilcoxon signed rank test. A 2-sample t-test has non-parametric analog the Mann-Whitney U test. And there's another test called the Wilcoxon rank sum test that has a different test statistic, but which is equivalent to the Mann-Whitney U test. And it's equivalent in the sense that they'll give you the same p-values for the same data set. So our basic idea behind the Mann-Whitney U test is we're going to compute the ranks of the data, same as we did for the Wilcoxon signed rank test. So the smallest value is going to get a rank of 1, second smallest is going to give it a rank of 2, and so on. And the benefit of working with ranks, both here and in the Wilcoxon signed rank test, is that ranks reduce the effect of outliers. That we no longer care whether the smallest value in this data set is 0 or 35, like one smaller than the next smallest value. All we care about is that it's the smallest value. So that reduces the impact of skew. And then the idea is that if the data in both of the groups came from the same distribution, then we expect the groups to have approximately equal sums of the ranks. So let's think about how we can use the ranks to give us a p-value. So suppose we're in a simpler example where we just ended up with all of the ranks in class 2 being the 5 smallest values. So let's see, class 2 got all of the lowest scores, and then class 1 got all of the highest scores. And we want to think about what p-value would correspond to that. Take a moment to think about how you might approach that. Thinking about techniques from early in Math 346. Any ideas? None?
I only guess order statistics.
Order statistics is a good idea, but we can actually do it more simply because with order statistics, we need to know what the distribution of the values were. We can actually do this more simply by taking an idea from the start of Math 346 and think about, suppose we have the numbers 1 to 10 as our ranks. And we're trying to find the probability of class 2 has all of 1 to 5 or something more extreme. This is given that the groups actually have the same distribution. Well, assuming there aren't any ties, there's nothing more extreme than just all of the lowest scores being in one class. So we're really just looking for the probability that class 2 has all of the 5 lowest scores. And if the 2 groups have the same distribution, then there's no difference between the 2 classes. We can just think about these numbers from 1 to 10 being like playing cards that we're shuffling up and then dealing into two piles. So we can find this probability using counting methods. We can say that this is going to be the number of ways to get 1 to 5 in one class and 6 to 10 in the other. Divided by the total number of ways to shuffle up the 10 cards between the two classes. Divided by the number of ways to arrange the numbers 1 to 10 in two groups of 5 each. Let's see. And then maybe let's think about just having class 1 be before class 2. So we're just dealing out 10 cards in order and then putting a dividing line between them. Where's my eraser? For our denominator, we'll just have the number of ways to put 10 cards in order. What's that going to be? Yeah. So we can think about for the first student, there are 10 choices of what card they get. For the second student, there are 9 choices and so on. For the numerator, how many orders are there to give the numbers 6 through 10 to the first class? Right?
Choose 5.
I think we can get there from here, but instead of, to make it consistent with how we're thinking about the denominator, let's think about ordering the cards rather than choosing them. Okay?
Is it 5 factorial?
Yeah, so we're saying we want these 5 cards to go in class 1. So now we're just worried about what's the number of possible orders is 5 factorial for the same reason as the denominator is 10 factorial. Times, how many orders are there for class 2 to get the numbers 1 through 5?
Is it 5 factorial?
Also 5 factorial. And then there's one other thing, which is that it would really be equally impressive to have the numbers 1 through 5 in class 1 as to have them in class 2. So if all we care about is testing whether there's a difference between the classes, not testing whether class 2 is worse than class 1, then we're interested in a two-sided test. So there are actually two ways that we could order which class does better. So this would be our p-value if we had all of ranks 1 through 5 in one of the two classes. Questions about this? All right. Counting method calculations always get kind of detailed and difficult to keep track of. And you can imagine that this would get a lot more complicated if you had to account for, okay, well, what would be equally extreme as having 1, 2, 6, 7, and 10 in class 2 versus in class 1. So typically what we're going to do is use the ranks to compute an approximate p-value using a table similar to what we did for the Wilcoxon signed rank test. So let me show you how to do that. All right. So the hypotheses for a Mann-Whitney U test are going to be the same as the hypotheses we had for a paired test using a Wilcoxon signed rank. Can someone remind us what those were?
The population distributions of X of X and X of X are identical.
Yeah, that's our null hypothesis. And the alternative hypothesis is that the distributions have different locations or centers. And just like the Wilcoxon signed rank test, if we are willing to assume that the population distributions have the same shape, then we can think of this as a test of the medians. So the null hypothesis would be that the population distributions have the same median. So of course, if they have the same shape and the same median, then they're also identical. And the alternative hypothesis would be that the population distributions have different medians. So to compute our test statistic for the Mann-Whitney U test, we're going to let sample 1 be the smaller sample, the one with fewer observations in it. If they're the same size, like in this problem, then you can choose arbitrarily. And then our test statistic is U, which is equal to N1 times N2. So these are the sample sizes from group 1 and group 2, plus N1 times the quantity N1 plus 1 divided by 2, minus W. And W is the sum of the ranks for sample 1. So try using this to find the test statistic for our reading scores problem. So problem 2B. Oh, and for simplicity, let's go ahead and say class 1 is sample 1, because we can choose arbitrarily because there's the same sample size.
But yeah.
All right, So we start by assigning ranks to each of the values. So 0 gets a rank of 1 because it's the smallest. 84 gets a rank of 10 because it's the biggest. We do have some ties. So 55 is tied for 4th and 5th place. So it gets a rank of 4.5. And 72 gets a rank of 8.5. So then W is the sum of the ranks in sample 1. So if we choose that to be class 1, then we get W equal to 36. And then U is 5 times 5 plus 5 times 6 divided by 2, and then minus W. So that ends up being 4. Oops. All right. So then our p-value, the way we compute it is going to depend on what our alternative hypothesis was. If our alternative hypothesis was that population 1 is greater than population 2, in other words, that population 1 is shifted to the right of population 2, that's sort of the easiest case for computing the p-value. So this would be if we were starting from the alternative hypothesis that class 1 is better than class 2, has higher reading scores. In that case, we can directly use the p-value from table 8 in the back of our book. So here's what that looks like for n sub 2 equal to 5. So start by looking at the portion of the table that corresponds to the size of group 2. And then we want to look at the column that corresponds to the sample size of group 1. So in our case, sample 1 also had 5 observations. So we're looking at this last column. And then our test statistic was 4. So that's the row that we look in. So our p-value is 0.0476 if we're doing this as a one-sided test. If your alternative hypothesis was that population 1 is less than population 2, or in other words, that population 1 is shifted to the left compared to population 2, then our p-value would be the probability that our value of U is greater than or equal to whatever we got in the data. And that turns out to be the same as the probability that U is less than or equal to N1 times N2 minus the test statistic. And that works because U is symmetric around half of N1 times N2. So in this case, we would have N1 minus, or N1 times N2 minus the test statistic. So 5 times 5 minus 4 would give us a value of 21. And then we'd be looking for what p-value in the table corresponds to a test statistic of 21. So here's our same table from before. And 21 is not on this table. So we go all the way to the bottom and say, if our test statistic was 12, then we'd have a p-value of 0.5. So here with the test statistic of 21, our p-value is greater than 0.5. And that should make sense because we just saw on the previous slide that if we're testing whether class 1 is better than class 2, we got a p-value of 0.0479 something. Oh. Yeah, 0.0476. So this is the opposite. This is testing whether class 1 is worse than class 2. It makes sense that we would have a large p-value. We would not have evidence to support the idea that class 1 is worse than class 2, because we already said that we had evidence that class 1 is better than class 2. All right, and finally, if we're testing a two-sided alternative hypothesis, just that the population distributions are different, then we take the minimum of the test statistic and N1 times N2 minus the test statistic. And use table 8 on that. And then we multiply by 2 to get the p-value. So here, the minimum of 4 and 21 is 4. And using the table, we saw that 4 corresponded to 0.0476. So our p-value for a two-sided test is 0.0476 times 2, so 0.0952.
Oh my God.
Any questions about this? All right, thank you for your attention. I will see you tomorrow upstairs in the lab.